Hello everyone, Math Cat here. Today we will be discussing the Gauss-Jordan elimination method to then get to reduced row echelon form. If you're focused on purely computational methods, then feel free to skip ahead to the chapters listed below. Alright, so let's take a look at these two matrices. Do you remember what kind of matrix this matrix is in? Take a moment to figure that out. This is called an augmented matrix. Notice that there's a line here. If we convert this back into its original form, we get 3x plus 5y plus z is equal to 3, and then so on and so forth. 2z equal to 2, and then z is equal to 4. So if you don't remember the conditions for row echelon form, there just needs to be a non-zero leading pivot in every row, and it needs to form a staircase, and there needs to be zeros underneath every single pivot. Now, is there anything different that you notice about this augmented matrix? This is in reduced row echelon form. Let's identify the criteria that qualifies or that lets a matrix be in reduced row echelon form. So, first criteria, every leading entry, let's write that down. Every or the leading entry in each non-zero is 1. So if you look at every pivot or the non-zero leading number in every row, you'll notice that it's 1. It'll never be in, like, this can't be 3, this can't be 10. Each pivot has to be 1 in each non-zero row. Okay? And for reduced row echelon form, it follows the same principles as row echelon form. And in this case, they need to be like a staircase. So each pivot is to the right of the pivot above it. This is to the right of the pivot above it. So it forms a staircase pattern. And now here's the important distinction. Yeah, we should probably write that down. Each pivot is to the right of the pivot above it. Okay? So, notice how there is a lot of zeros here. You'll learn later that this is something called the identity matrix, but let's just focus on reduced row echelon form for now. Notice that there are zeros under each pivot, similar to row echelon form. There are zeros underneath each pivot, but there are also zeros above each pivot. So zeros above and below. Alright? And let's write that down. So a more precise way to define it is that each pivot is the only non-zero entry in its column. So the only non-zero entry. Okay. So these are some of the main criteria that define reduced row echelon form. There's also one more criteria. If this matrix had like zero, an entire row of zeros, then it adds another criteria to reduce row echelon form. If there is ever a row of zeros anywhere, like let's say the row of zeros was this row, all 0 rows need to be at the bottom. So if you remember, you can manipulate systems of equations, you can move them around, do whatever you want to them. Same thing applies here. All 0 rows need to be at the bottom. Does that make sense? All right, let's go on to identifying some matrices in the form of row echelon form or reduced row echelon form. Let's try and identify. Let's say you have a matrix 1, 2, 1, 0, 0. Okay, let's say you have this matrix. Would you classify this as reduced row echelon form or something else? Well, if you asked me, I would identify this as reduced row echelon form. Why? Because if we take a look at each pivot column, or every column that has a pivot, there are zeros. It's the only non-zero component in its column. Notice that this row or this column doesn't have a pivot. This one has a pivot. This one has a pivot. And each pivot is to the right of the pivot above it. This pivot is to the right of this one. So it forms a staircase pattern. And if there were any all 0 rows, well, there's no all 0 rows, so we can ignore that criteria. But then we also see that every pivot is 1. So the leading entry in each non-zero row is 1. Alright. And you might be wondering, what is this? What is this 2 doing here? This looks weird. This is something called a free variable. So that means that if we write out the solution for this, x plus 2y is equal to 2. Let's do z is equal to 1. And let's do w. And then let's do z is equal to 3. So I'm defining this as w, this as z. Notice how y doesn't have a unique solution. That means that a fixed value of x, because x is a pivot, plus y could be anything. So y is equal to y. And these are the, well, let's rewrite this. X is equal to 2 minus 2y. These will be the solution for this matrix. So you can identify that this is a free variable. These have unique solutions. This has a unique solution, but again, y could be anything. Oh, I didn't mean to circle this earlier. I'm sorry about that. But these have unique solutions, but y can be anything. That is basically what a free variable means. So maybe geometrically, every free variable adds one whole dimension of solutions. So maybe for this, there we have one free variable. That means y could be anything, y could be any value. So it adds an entire line of solutions. And let's say if you had another free variable, that would turn that line into a plane. If there was two free variables, make a plane of solutions, that would work. There's not a specific um specific values that make the equation true. Any value that is defined by this line makes the equation true. So instead of just dots that work for the equation, it's an entire line, entire plane. If you have two free variables or maybe three free variables, you have a full cube of solutions. So a quick rule to remember this is the amount of free variables is equal to number of unknowns minus number of pivots. So if you look here, we have one free variable, but let's say we didn't know that. We can make a generalization. We have 1, 2, 3, 4 unknowns, right? X, Y, W, Z. And we have only 3 pivots. So we can for sure say that there will be one free variable because 4 unknowns minus 1 pivot, minus 3 pivots, this is equal to 1 free variable. Let's talk about possible cases for reduced row echelon form and what those cases mean. So there are 3 cases. Let's say you have this matrix. This is in reduced row echelon form, and we can see here that there is a row of zeros. If you ever see a row of zeros, you want to put it at the bottom, and that would mean that this has infinite solutions. Because 0 is equal to 0. If you write this whole thing out, x plus y is equal to 1, and 0 plus 0 is equal to 0. 0 equals 0. Infinite solutions. Okay? Now, let's take a look at second case. You will see that if you write this out, x is equal to 3, y is equal to 1, because 1x is equal to 3, y or 1y is equal to 1. You will see that each variable has a unique solution. So this matrix has one unique solution. Now let's take a look at the last example. So if you write this out, you immediately see that there's a contradiction. This z here saying it's equal to 0. Actually, no, this should be switched. I'm so sorry. You'll see that it says like 0x plus 0y plus 0z is equal to 1. That's impossible. So there's a contradiction. It doesn't make sense. Therefore, there's no solution. Okay? Now, here is a case that I would like to cover. If you ever get something like this, you'll see that there is a 0, 0, 0 row. That usually means that there's infinite solutions, right? But because there's a contradiction up here, that immediately overrides that infinite solutions. So this matrix has no solution. The contradiction will always override any matrix, causing that to be no solution. Is this in reduced row echelon form? Well, I would say that yes, this is in reduced row echelon form because there is non-zero pivots in each column. So for this one, but there is also an entire row of zeros and it's at the bottom. Okay, and we can count the amount of free variables. Again, let's do number of unknowns minus number of pivots. There are 3 unknowns, x, y, z, and there are 2 pivots. So that means there is 1 free variable. So it could be z. And you set that equal to itself, and that is an entire line of solutions. Isn't that cool? Okay, let's move on. So given a matrix, we want to convert this to reduced row echelon form. First, let's convert it to row echelon form. You must convert a matrix into row echelon form before you actually start computing into reduced row echelon form. Okay? So let's get rid of this second row here by, let's start by multiplying the bottom row by -2. So row 1 minus 2, row 2 is equal to the new row 2. 2, 4, 8, and then -2 times 1 is -2, and that means 2 minus 2 is 0, so that becomes 0, and then 3 times -2 is -6, plus 4 is -2, and then -2 times 7 is -14, -14 plus 8, that should be what is that? -6. Okay. And notice how everything here is divisible by 2. So, this is equivalent to this. Now, how do we, this is in row echelon form, but how do we actually reduce this into reduced row echelon form? Well, we want to get rid of this up here. We want to get this pivot down here to be the only non-zero entry. So we can take row 2, multiply it by 2, and add it to row 1 to get the new row 1. Okay? So 2 times 0, that is unchanging. Let's write the bottom row first. 2 times -1 is -2 plus 2, that is 0. -3 times 2, -6 plus 4 is -2, right? Or no, -2. So now we can identify that this is x, this is y. X is equal to -2, and -y is equal to -3, which is y is equal to 3. And this is your solution. Does this have infinite solution, a unique solution, or no solutions? Well, this is in the form of unique solutions. We just identified those. Now, let's practice with a 3x3 matrix. Okay? Actually, I lied. 3x4 matrix. Okay. Now, let's see. This is already in row echelon form. Let's try and get this pivot to 1. So 1/2 of row 3 is equal to the new row 3. Now this is, we have the pivots as 1. Now we just want to get rid of these. So let's start from row 3. So we can multiply row 3 by what? By -2. And then we add it to row 2. And that gets us our new row 2. Okay. 1, 2, 1, 8. And then 0 times -2 is 0. And then -2 times 1 plus 2 is 0. And then -2 plus 2, or sorry, -2 times 2 is -4, plus 7 is 3. And then we want to get rid of this one up here, so we can just do row 3, or minus row 3, plus row 1. And that gets us, that removes that 1 up here. So then this pivot can be alone in this column. So 1, 2, 0, and then -2 plus 8 is 6. Now we only need to get rid of one more up here. How do we do that? We utilize row 2. Row 2, or two of those, negative 2 times row 2 plus row 1 is equal to the new row 1. 0, 0, because the negative 2 sums 1 plus 2 is 0. And then everything is 0. So then negative 2 times 3, which is negative 6, plus 6, that is 0. Now we have our solution set. Does this have one solution, one unique solution, infinite solutions, or no solutions? I'd say it has one unique solution because every variable has its corresponding output and there's no contradictions. Now let's test your concepts. Let's say you have a matrix without row reducing. Explain why the system must have infinite solutions. Well, you can see here if we add two of these, we do negative 2 row 1 plus row 2 to get the new row 2. You will see that if you once you perform this operation, apply negative 2 to everything, you'll get this row of zeros, which you can then move to the bottom, and 0 is equal to 0. This has infinite solutions. Let's test another concept. Let's say you have a 3 by 5 augmented matrix. It has 3 pivots. How many free variables are there? Well, we can use this formula or this, I guess this formula. The number of free variables is equal to the number of unknowns minus the number of pivots. So a 3 by 5 matrix has 5 unknowns because if you expand it out, you have 1, 2, 3 rows and 1, 2, 3, 4, 5 columns. 5 unknowns. Actually, I'm sorry. It actually has 4 unknowns because this is an augmented matrix. I forgot to consider this equals here. So you actually have 1, 2, 3, 4 unknowns and 1 output here. So there are 4 unknowns and 3 pivots. That means there will be 1 free variable. Let's test one more concept. Let's say a system has more equations than unknowns. Does that guarantee a unique solution? Let's say you have something like this. Well, you'll see that there's a redundancy. There are 2 unknowns but 3 equations. This is just a multiple of this. So it doesn't exactly guarantee a unique solution, because I mean, this could have a unique solution, but let's say you have something like this. There's a contradiction, and that means there is no solution. Or let's say you had 1, 2 equal to 100. This, this, this is a contradiction. They don't equal each other. Doesn't make sense, right? There's no solution. So a system having more equations than unknowns does not guarantee a unique solution. Nice. Hello everyone. Thank you guys so much for all this fan art, and I really appreciate the time that you guys put into supporting me. And I want to apologize for the lack of uploads or the lack of consistent uploads, since school has been pretty rough. Differential equations is starting to ramp up, as well as some of my other classes. So I will be trying my best to finish the linear algebra series, but do know that uploads will slow down for now. I hope to start back up again, kind of like consistently uploading maybe nearing the summer, where I have more time to make these types of videos. But yeah, if you want to support me, please go check out my Ko-Fi. And as a reminder, I always have some extra art and lecture notes available on my TikTok and Instagram. And if you want to support a fan art and be featured, please fill out the fan art submission form below. Thank you so much for watching, and I appreciate you so much.